When you're talking about circular motion or energy, one of the fun things to always discuss is a roller coaster going through a loop. So I wanted to take a look at that based on some data and a video I took of the Batman roller coaster at Six Flags New England in the spring of 2017. I did the best I could to make the camera head on so it was perpendicular to the loop. It's not perfect, but it's pretty good. Let's take a look at the video. So we'll try to analyze the car as it goes through the loop, and notably at locations on the side and the top. And I guess on this side too. So you'll notice that it's not a circle, it's actually a teardrop. We can consider the motion the car is going in any one place on the circle to be like circular motion, because there is a centripetal acceleration. But comparing two places as if it's on a circle is not going to be accurate. We'll go into some of that in some classes and why they would do it like that. I think the first thing that would be worth doing would be to look at the forces that are on the roller coaster as we go through the circle. So clearly we have a force of gravity. That's always pointed down, and it's always the same. The other force we have is a normal force. And it's always pointing inward. Oops. So that makes this motion a little bit complicated. It's not uniform circular motion because gravity is always pointing in the downward direction. It's providing a centripetal radial acceleration up here at the top, but it's providing tangential accelerations here on the side. So the car is speeding up and slowing down, which I think you saw from the video clip. That means that the acceleration is not always purely centripetal. I plugged this into Tracker, and I'd like to show you what Tracker calculates for its accelerations. I have to give credit to two of my students from 2016-2017 for figuring out how to make this awesome image. They spaced out the frames a little more, so they only looked at every fifth frame, I believe, and then they figured out how to do the acceleration vectors on the picture. But what you can see in it is that at the top, where both forces were inward, we see the inward acceleration that we would expect as you move through a circle. But as you start to go down, remember over here, gravity is no longer a radial force, it's a tangential force, it's down. We see an acceleration that's partly inward, but also partly down. And what that means is that the cart is not in uniform circular motion, it's actually speeding up because gravity's speeding it up as it comes down. So just treating this as a circular motion problem is not the most effective. When you're dealing with a vertical circle, the concept of energy and energy conservation can be a really helpful concept. Since the car is speeding up and slowing down, and it's changing its height, conservation of energy seems like a really good way of studying it. So, in order to do that, we would typically write our conservation of energy statement. And at any given time on the circle, which we'll call EO, we'll call some early time on the circle EO, the car has kinetic energy, and it also has potential. And at any later time as it goes through the circle, it still has kinetic and it still has potential. We can plug in our equations, our energy equations. And as we often see, one of our terms cancels out, mass. This is actually really fortunate in this case because I don't have any idea what the mass of a roller coaster car is. That's not information Six Flags releases. So it's pretty good at cancels. And we're left with a usable equation that relates speed and height at any two times along the circle. So this is our output data from Tracker. I've copied it into a spreadsheet. And you can see it gives us time, x position, and y position. So that means we're only going to be able to get, at first at least, x velocity and y velocity. So you can see I've put in the slope equation under the column I labeled velocity x. So I'm subtracting position 2 minus position 1 or time 2 minus time 1. I'll then calculate all those and I'll do the same thing for the other column using y position instead of x. So I've got my velocity in the x dimension and in the y dimension, and what I need for kinetic energy is I need my speed. So how do we calculate our speed? Let's take a look. Again, the v in kinetic energy is speed. It doesn't care about direction. It's not a vector. So in order to get our x velocity and y velocity usable for kinetic energy, we have to add them together using the Pythagorean theorem. C squared equals a squared plus b squared. So that's what I'm doing in the next step. So I have most of the Pythagorean theorem plugged into this column labeled velocity squared. Notice I actually haven't square rooted it like you usually would if you were calculating the side of a triangle. Since the formula for kinetic energy has v squared in it anyway, it's not worth doing that just to re-square it. So I'll calculate all those v squareds, and then you'll notice I have three columns. I have kinetic energy divided by mass, potential energy divided by mass, and total energy divided by mass. We saw from the conservation of energy equation earlier that we can take the mass out since it was in every term. We don't know what kinetic, potential, and total energy are for this roller coaster since we don't know the mass, but we know these quantities. And we can use them to track how energy changes relative to each other as you go around the circle. So here's my calculation of the kinetic energy term. Since we already did the v squared part, we just have to multiply it by half. Here's my calculation of the potential energy term, which is GH since we divided by mass out. So I just did 9.8 times all the data in column C, which is representing our height. Because we picked the top of the roller coaster to be height 0, all these potential energies will be negative, but with potential energy you could pick any 0 point you want and the equation is still valid. So now for our total energy, of course, we're just going to add the term representing kinetic energy and the term representing potential energy together. And now I'm going to make a graph of time versus the three types of energy as we go around the loop. So here's our final data graphed, and it's a little confusing to look at first because of potential energy being calculated from the top of the loop. That means potential energy is always negative. But you could see that just like we saw before with the marble on the track, the potential energy curve is a mirror image of the kinetic energy curve, which means that as one rises, the other falls. So we're seeing that energy is for the most part conserved as we go around this track. There is one tiny thing that makes us think it's not entirely conserved, and that is if you look at the yellow total energies, a best fit line for them would be slightly downward, which represents a little bit of energy loss. Let's discuss that. So as you could hear in the clip, the roller coaster makes noise, and that's because there's pieces of metal rubbing on each other. And that's going into making noise, but also heating up the air around it. And those represent losses of energy. You can see it's not a very severe loss. The potential and kinetic energy curves are still very close together, and it's only a slight downward slope. But the roller coaster does have energy leave the whole time because of friction. So how could we alter our original energy equation to account for the frictional force? Well, we can't use this one where we cross the m out. We have to go back to the one just above. So let's kind of uncancel that dividing out. And as we saw, there was some non-conservative work being done by the force of friction that was removing energy from the system. The easiest way I know to account for that in the equation, a way that was actually suggested to me by a student a few years back, is to put a term on this side of the equation representing that non-conservative work. And since it's actually taking energy out of the system, we'll put a negative there. That'll tend to make this side more negative or smaller, which means this side will be smaller, and we'll see a smaller amount of energy over here. So you can still use the idea EO equals EF if you've got non-conservative forces. You just have to account for them with another term. The suggestion my student had, and I've used it ever since, always put it on the left side. Negative if it's taking energy out of the system. Positive if it's adding energy to the system. So if someone was giving an extra